Okay, so first of all, what is a field? We're going to be talking about electric fields, but in general, what is a field? Do you remember the idea of a function from algebra? If you've got an input and this function creates an output, maybe you take the input and square it and add 3, or maybe you take the input and take the cosine of it and add 5 or something. It's just some process that turns an input into an output. And usually we expect the input to be a number and the output to be a number. A field is basically the same idea as a function, but with one subtle difference. The input is not a number, the input is a location. A field just assigns an output or a value to every location in space. So if you have any way of just assigning a number or some sort of value to every location in space, that technically counts as a field. For example, let's say you've got a map. What would be an example of a numerical value you could assign to every point on that map? For instance, let's say you've got a map of California. And by the way, it doesn't matter how bad your map of California is, as long as it's got the Tahoe angle and the bay, it's recognizable as California. Yeah, elevation is a good example. Every point on this map has an elevation associated with it. We could say like, this point is 20 meters above sea level, and this point is 22 meters above sea level, and this point is 30 meters above sea level. You could just start listing out numbers on the map, making sort of a grid. So elevation is a field. It has a value at each location on this map. Of course, just listing out the numbers is a pretty messy way to do this, because we just end up with this huge grid of numbers. It would be difficult to make, and it would be difficult to read, and it even still wouldn't really have enough detail as you might need. So how do we usually draw elevation maps instead? Like if you want to describe some region as having a certain elevation, how is that usually shown on a map? Yeah, a topographical map. Usually the way we do that is that presumably there's not just going to be one location whose elevation is 20 meters above sea level. There's going to be a whole region that's got location or elevations of 20 meters above sea level. So a topo map typically looks something like this. You're tracing out a curve representing all the locations whose elevation is 20 meters. And then you have another curve representing all the locations whose elevation is 25 meters. And then another one at 30 meters. And then maybe another one at 15 meters, and so on. So you're looking at a topo map like this. If a point is on one of those curves, you know that that point has altitude 20 meters or whatever is associated with that curve. If you're looking at a point somewhere in between, you can't tell exactly, but you know this point has an altitude somewhere between 15 and 20 meters. So this is a very convenient way of depicting a field like this, showing the values of all the locations without listing out just this really tedious grid of numbers. So a topographical style map is a very useful way of drawing a field, depicting it visually. Any questions on that so far? So that's one example of a field, just assigning a number, in this case elevation, to every point on a map. What are some other values you might want to measure at every location on a map? Like think of a weather report, for instance. What are some values that might be useful to depict on a map in a weather report? Yeah, wind speed, for instance. If you care about wind, you might display that data as a map that depicts wind as, maybe you could just list out a bunch of numbers showing wind speed. But the thing is, for wind, the speed is not the only thing that's important. You want to know the wind is going to be blowing at 10 miles per hour, and also what else would you want to know about the wind? Yeah, you want to know which direction it's blowing. So that means that this is actually a vector quantity, the velocity of the wind, the speed and direction. And so at each location on the map, we'd have not only a numerical value, we'd also have a direction associated with it. And that would usually just be drawn as a bunch of arrows. So this would be an example of what's called a vector field. Maybe the wind in the state looks like this. So wind velocity is an example of a vector field as opposed to a scalar field. A scalar field means we're assigning a number to each location in space. A vector field means we're assigning a vector quantity, a magnitude and direction to every location in space. So wind velocity would be a vector field. Temperature, for instance, would be an example of a scalar field. Or elevation, if you're just assigning each location with a number for the temperature of that location at that time. But if it has a direction associated with it, it would count as a vector field. Any questions on that so far? And for vector fields, one way to depict it is by just drawing a whole bunch of arrows. But that can be pretty tedious as well. It's difficult to draw. You have to draw all these little arrows. It can be difficult to interpret visually by looking at it. So usually what we do instead is we draw what's called a vector field line. The field lines are just curves following the general trend of the vector arrows. They don't have to actually connect all the arrows, because where you place the arrows is kind of arbitrary. But the vector field lines should be curves following the general trend. So a curve with arrowheads on it showing direction, showing the general tendency of these arrows. So instead of drawing out all the individual arrows, we would just draw curves representing the trend, and then arrowheads showing the direction they're pointing. Any questions on that field line diagram so far? And ideally, this is supposed to be representing the same information. Drawing the field arrows versus drawing the field line curves is just two different ways of drawing the same thing. Kind of like the difference between a ray tracing diagram versus a wavefront diagram for wave travel. You do lose a little bit of information though, because the field lines tell you everything you need to know about the direction the vectors are pointing. But a vector isn't just direction. What other information does a vector have other than just direction? Yeah, the magnitude. The field lines are kind of missing the magnitude information. The field lines very accurately depict the direction the vectors are pointing, but you kind of lose out on how big the arrows are. So the way we depict that for field lines is if the vectors are very strong, very large magnitude, we depict the field lines as close together. If the vectors are weaker, smaller magnitude, we would depict the field lines as further apart. So for example, if we draw out a vector field, if we draw the field lines like this, let's say we have a vector field that is drawn like this. This region has the field lines packed very closely together. That symbolizes that the vector field is very strong in that region, large magnitude. Over here, the field lines are spaced further apart. So that represents that the vector field has a weaker magnitude. Smaller, if we drew it as arrows, they would be smaller arrows. So this is the way we handle notation in field line diagrams. Lines further apart represent a weaker magnitude. Lines closer together represent a stronger magnitude. And that's usually referred to as the density of the field lines in terms of how many field lines per centimeter. Any questions on the notation there so far? So let's take a look at how this applies to electrical phenomena. If we have electrical charges and they're exerting forces on each other. In the simplest case, let's say we just have two charges. Is magnitude same as density? I wouldn't really say they're the same thing. It's just that the density, the number of lines per centimeter or whatever, is how we represent magnitude. So magnitude is how strong the vector is, or how fast or how far, whatever the vector is measuring, the numerical value. And then density is how many field lines per centimeter or per whatever distance. So we use the density of field lines, how close packed they are, to represent the magnitude of the phenomenon. So let's say we have a couple of charges. Let's say a positive charge, positive Q1, and another positive charge, positive Q2. What would you expect these charges to do to each other? Yeah, they're going to repel, which means there's going to be forces involved. You're going to have charge 2, for instance, is going to experience a force in which direction? Yeah, charge 2 experiences a force to the right. So this would be the force on 2 from 1. And meanwhile, what's happening to charge 1? Charge 1 experiences a force to the left. So this would be the force on 1 from 2. So we've got two forces involved, the force on object 1 from object 2, and the force on object 2 from object 1. And what should we assume about the magnitude of those two forces, how strong they are? Think back to Newton's laws from physics 7b. Force on object 1 from object 2 and force on object 2 from object 1. What should we always assume about those forces? Yeah, these are equal and opposite forces. These are exactly the equal and opposite forces that Newton's third law is talking about. In fact, this is just Newton's third law. Newton's third law, the idea of forces coming in equal and opposite pairs, that if objects are interacting with each other, then the force that the first object exerts on the second object is the exact opposite of the force the second object exerts on the first object. So they're the same strength, but in opposite directions, because these forces really just represent the same interaction viewed from two different perspectives. So we don't really need to calculate two different forces. These are just a single force, but viewed from two different perspectives. And in many cases, we don't really care about both of the forces anyway. There's a lot of situations where one of the objects, either it's staying still anyway, maybe it's rooted in place by other forces, maybe it's attached to something larger, or maybe it's so massive that it's hardly going to move at all, or maybe it does move, but we don't really care about it. There's many situations where we only care about the forces acting on one of the charges, one of the charged particles. And typically we call that the test object. So we're often going to treat this as what we call a source charge creating some effect. And a test charge or test object experiencing that effect. So that's the notation we're going to use, the terminology. And I want to emphasize that this is not talking about what's really happening. This is not creating some effect. This is not experiencing some effect. What's really happening is these objects are exerting forces on each other. But it's often mathematically useful to think of it as one of the objects doing something and the other object experiencing that something. And so that's the notation we're going to use. We're going to treat this as if one of the objects, which we'll call the source charge, is creating some influence in the space around it. And the other object, which we're going to call the test charge, is experiencing that influence. And this is completely symmetric. We could instead treat this charge as the source creating some effect, and this charge as the test object that's experiencing that effect. It doesn't really matter which one you call the source charge and which one you call the test charge. It's really just a matter of which object do you want to figure out more information about. So usually you would, if there's some object where you want to find the forces on that object, you would treat that object as the test charge, and then everything else influencing it as the source charge or source charges. Any questions on that so far? So let's look at the extreme case there. Let's say we have a source charge that's just some really large charge far away. We don't care about its motion. We just care about what it does to everything else. So let's say far off in the distance, we just got some enormous positive charge. And by the way, we use both capital Q and lowercase q to represent charges. Often we use capital Q for a source charge and lowercase q for a test charge. That's not universal, but that's usually the way it's done. And let's say we have a charged particle over here. And let's get some actual values here. Let's say we have a, let's say positive 12 coulombs. We put this charged particle here. This is positive. We'll call this the test charge or test object. This test object has a positive charge. The source charge is also positive. So what are these objects going to do to each other? They'll repel. The test object experiences a force to the right. The source object also experiences an equal and opposite force to the left, but we don't care about that. We're just going to look at the force on the test object. So that's going to be some amount of force to the right. And let's say we measure that. We measure this force and we find that it is, let's say, 18 coulomb or 18 newtons. So we measure the amount of force on this particle. We find that it's an 18 Newton force. And let's say we now swap this out for a different charge. We want to try this experiment with several different charges. So we remove this one from the situation. And at the same location, we put a different charge. Let's say a 6 coulomb charge. That's also going to experience a force. But how much force would you expect that one to experience? If the 12 coulomb charge experiences 18 newtons of force, how much force would you expect 6 coulomb to experience? 9 newtons. And why is that? Why would we expect this one to experience 9 newtons of force?
I was just thinking that because the 6 is half of 12.
Yeah, that makes sense. 6 coulombs is half of 12 coulombs. If it's experiencing force because it has a charge in the first place, then it's reasonable to think that half as much charge leads to half as much force. And in fact, that is exactly what happens. This particle with half as much charge experiences half as much force. I should probably label these force. And likewise, if we had a charge that was, let's say, twice as much, 24 coulombs, how much force would you expect that to experience?
Is it 36?
That makes sense. Twice as much force should suggest twice as much charge means twice as much force. So here the force would be twice 18, so that'd be 36 newtons. Or alternatively, what if we had, let's say we had a negative charge. Let's say negative, let's make this negative 4 coulombs. First of all, the force would be in which direction?
To the left.
Force would be to the left. And also to figure out the amount, how would you estimate, or how would you calculate how much forces would experience? What would you compare it to there?
Could you maybe do it to the 24 or the 12 coulomb one?
You compare it to any of these, really. For instance,
Okay.
4 is what fraction of 24?
1 or times 6.
Yeah, 4 is 1/6 of 24.
Yeah.
If it's 1/6 as much charge, we should expect 1/6 as much force as well. So what would be 1/6 of 36?
6.
Yeah, so this should be a 6 Newton force to the left. And we could also compare it with these, for instance. 4 is 1/3 of 12, and 6 newtons is 1/3 of 18 newtons. Or 4 is 2/3 of 6, 2/3 of 9 newtons would be 6 newtons. So we're basically assuming a proportionality here. And again, this is in fact what actually happens, that the force is proportional to the charge. The electric force on this test object is proportional to the charge of the test object. These objects all experience different forces because they all have different charges, but force and charge are proportional to each other. In the sense that, for instance, twice as much charge means twice as much force. 1/6 as much charge means 1/6 as much force, and so on. Any questions on that so far?
Okay, so I have a quick question. So if we have a problem like this, would they give us like at least 2 of the 3 quantities that we need? Like they would give us the coulombs and the newtons on like the question?
Yeah, something like that. Like in this case, I mean, this isn't so much a practice problem or a quiz problem, for instance. This is more investigating just how these forces interact with each other.
Okay.
But if you have, like in this case, we knew this charge and this force, so we can infer that half as much charge leads to half as much force.
Right.
And of course, that's only true for the fact that it's at this location. If we moved it to a different location, it would now be closer to the source, so it would experience a different force.
Oh, okay.
But
Okay,
the
thank
idea
you.
is we're changing just one thing. We're just changing the charge we're using as the test object and keeping everything else the same, and we see what happens. If these things are proportional, though, in general, we can always write that as an equation. If we've got 2 variables that are proportional to each other, like let's say y is proportional to x, how could you write that proportionality as an equation? If y is proportional to x, we can write that y equals what?
X times a constant?
Yeah, x times some constant. So we can do the same thing here. If we're claiming that the force is proportional to the test charge, then that means we should be able to write that the force, electric force, equals the test charge times something. So there's going to be some value, some constant that you can just multiply by the charge to get the force. And that something is what we call E, the electric field. So E here, the quantity we're calling the electric field, is just the thing you multiply by the test charge to get the electric force on that test charge. It is essentially a constant of proportionality. And what would you expect the units to be there? What is charge usually measured in?
Is it volts? Or
Well,
coulombs?
we were using coulomb.
Yeah, coulomb, sorry.
Volts is going to become important as well, but formerly volts is joules per coulomb. It's an energy density. It's how much energy per unit of charge. And that's actually the same volts we were looking at with electrical circuits at 7B. So it's going to tie into this in the sense of the relationship between energy and charge. But force isn't measured in joules. What is force measured in?
Newton.
Yeah, force is measured in newtons. So to make this all match up, what does electric field have to be measured in?
Newtons over coulombs.
Yeah, so newtons per coulomb is the unit of measurement for electric field. And it turns out that that's also the same as volts per meter. So you might also see electric field measured in volts per meter. But for now, we're going to write it as newtons per coulomb. And as far as I know, nobody has seen fit to name this as an abbreviation after some 19th century physicist yet. So it's still just called newtons per coulomb. But that's the units of measurement we would use. And we can actually calculate electric field. Anytime you're defining a new quantity, it's a good idea to try solving the formula for it to see what it actually means. Oh, first of all, one other question. Should we treat E as a vector or a scalar here?
A vector.
Yeah, it's got to be a vector because force is a vector and charge is definitely a scalar. It's just 12 coulombs. It's not like 12 coulombs to the northeast. So if this is a scalar, electric field has to be a vector so that we can establish a direction. Because if you got a vector times a scalar, you get a vector. So electric field has to be a vector since force is a vector. If we want to figure out more information about electric field though, how would you solve for electric field? How would you isolate E in this equation?
Divide by the test charge.
Yeah, if you just divide both sides by test charge, you get the force divided by the test charge. So the electric field can be thought of as the ratio of the force that would be experienced by that test object divided by the charge of the test object itself. So we can actually calculate for each of these. For instance, for this one, if we just divide force divided by charge, force divided by charge would equal what?
One 1.5.
Yeah, 18 over 12 reduces to 1.5 or 1.5. So that'll be 1.5 newtons per coulomb. And since it's a vector, we need a direction associated with it also. So what would be the direction of the electric field here?
Would it be to the, to the right?
Yeah, because we've got this force vector to the right. We're dividing by a positive scalar. And if you multiply or divide by a positive scalar, you're not changing the direction at all. So the electric field is 1.5 newtons per coulomb to the right. What if we do the same calculation on this one? 9 newtons divided by 6 coulombs?
It's still 1.5.
Yeah, still 1.5. And 36 divided by 24, that's still 1.5. We got to be careful here. We're taking 6 newtons to the left, dividing by negative 4 coulombs. 6 over 4 still has a magnitude of 1.5. But what happens if you take a vector in some direction and multiply or divide by a negative scalar?
Does it flip the direction or no?
Yeah, exactly. The negative multiplier or divisor just reverses the direction completely. A scalar multiplier or divisor can't change which direction the vector is overall, but it can flip the direction exactly if the scalar is negative. So 6 newtons to the left divided by negative 4 coulombs equals 1.5 newtons per coulomb to the right. So the electric field, for all of these, they have different forces because they have different charges. But for all of them, the ratio of force over charge is exactly the same. Because this is really what proportional means. These values are proportional. Force is proportional to charge because the ratio of force over charge is the same for all these cases. So we don't even really need to say that, like for force, this force is associated with this charge. This force is associated with this charge, and so on. But the electric field isn't associated with any one of these charges. The electric field is associated with this location in space, whether there's a charge there or not. In fact, even if we didn't put any charge there, we could say that empty point in space has an electric field of 1.5 newtons per coulomb, which is essentially a description of the ability of that point in space to cause a force on a charge if there was one there. So even if we removed all the charges, we would say this empty point in space has the ability to cause a force on a charge if we put one there. And the force it would get is 1.5 newtons per coulomb of charge that it has. In fact, a very useful way of thinking of electric field, it's force divided by charge. What's the easiest charge to divide by? What's the easiest number to use as a denominator? Yeah, 1. So if you just think of the charge as 1, if you imagine hypothetically putting in a 1 coulomb charge here, if we just took out all the other charges, if we just put a positive 1 coulomb charge here, how much force would that experience? If we now know the electric field is 1.5 newtons per coulomb, and the force is just that electric field times the charge, what's this electric field times 1 coulomb?
1.5?
Yeah, 1.5 newtons. So a very useful way of thinking of electric field is the electric field is the force that would be experienced by a hypothetical positive 1 coulomb charge if it were put there. And note that you don't even need to have a charge put there in the first place. If this is just an empty point in space, you could think of the electric field as what force would be experienced by a 1 coulomb charge if you did put one there. So I think that's a very useful interpretation of what electric field is. The electric field is the capability of exerting a force on a charged particle if you put one there. And the fact that it's a property of that location in space is why we call it a field in the first place. A field is a value assigned to every location in space. This location has this value associated with it, 1.5 to the right. What if we move this particle closer to the source though? If these particles were all moved closer to the source, what would you expect to happen to the forces on them?
Would it increase?
Yeah, if the charged particles are closer together, the repulsive force would be stronger, or attractive force if we use a negative charge. But in general, the closer the particles are to each other, the stronger the forces become. So if you move all these closer, the force would be stronger, but we're still using the same charge. So we get a stronger value of E. So that means the electric field will be stronger if you're closer to the source, and likewise weaker if you're further away from the source. So this also ties into why we call it a field. It depends on your location relative to the source charge. Move closer to the source charge, you get a stronger electric field. Move further from the source charge, you get a weaker electric field. So it's really a description of all the locations in space around the source charge, describing to what extent is the source charge influencing that point in space. So the source charge creates an electric field in the region around it, and the electric field exerts a force on these test objects. Any questions on that idea so far? And let me actually write that out, because I think this is an important thing to consider in terms of how we're describing all this. Our general scheme here is that the source charge creates an electric field in the space around it. And that electric field causes a force on the test charge. And again, this is not what's physically happening. What's physically happening is the source charge and the test charge are exerting forces on each other. This electric field is basically just a mathematical construct, this imaginary idea that we create to make it easier to do the math. And this may seem like we're adding in an extra step. Like instead of saying the source charge exerts a force on the test charge, we're saying the source charge creates this fictitious thing called the electric field, and then the electric field creates a force on the test charge. But the advantage of this is that if you do this first step, if you say the source charge creates an electric field, once you've found the electric field, you don't need to care about the source charge anymore. We can basically just pretend that the electric field itself is what's exerting the force on the test charge. So if you've got some source charge or some collection of source charges, and you want to find the forces they exert on various other test charges, you don't want to have to do the calculation of source charge creating a force on the test charge over and over again. Instead, you can just do one calculation of the source charge creates an electric field. If you can figure out what that electric field is, you don't need to worry about the source charge anymore. You can just say that electric field creates a force on every test charge. All you need to do is multiply electric field times that test charge, and you immediately know the electric force. So it's really a shortcut in the sense that we're splitting up the process into several sub-processes. We're figuring out what's the electric field caused by this source charge, and then you can focus on the electric field exerting forces on the test charges without having to worry about the source charge at all anymore. Any questions on that so far? And a couple of formulas associated with that. If you know the electric field, you can find the force on the test charge just by using this idea. That to go from here to here, you can say force equals test charge times electric field. Or vice versa, just by dividing both sides by charge. On the other hand, this interaction, if you know the source charge and you want to find the electric field, this can be more complicated depending on how the source charge is arranged. The simplest case is if the source charge is just one single point object. Like if the source charge is just one tiny piece of charge, like a single proton or something, or even just the nucleus of a single ion, then we have a fairly straightforward formula for it. For a single point source charge, if all the charge we care about is concentrated at a single point in space, first of all, which direction would you expect the electric field to point? Like, let's say you're near a positive source charge. Would you expect the electric field to point in which direction here? Again, if we consider the electric field to be the force that would be experienced by a 1 Coulomb charge, if you just put a positive 1 Coulomb charge here, which direction would it get pushed or pulled?
To the right?
Yeah, it's going to get pushed to the right. What if we put it down here, like below the source charge?
Down?
Right, downwards. In general, it's going to get pushed away from the positive source charge. So generally, an electric field will point away from a positive source charge. Or if this was a negative source charge, all the positive charges would get pulled towards it. So electric field is going to be pulling inwards towards negative charges. So if you've got a positive source charge, we expect the electric field to be pointing away from it. So the field line, the vector field, if we draw it as field line diagram, would look kind of like this. You've got electric field pointing outwards in all directions. And notice that close to the charge, these lines are packed fairly close together. Further away, the lines are more spread out. And what do we say that represents? If the lines are more spread out or more close together, what does that signify? What is this notation saying? If the lines are very close together versus very far apart.
Does that have something to do with the magnitude?
Yeah, if the lines are very close together, that signifies strong magnitude. If they're further apart, that signifies weak magnitude. So in the region close to the source charge, these lines are close together, meaning we've got a strong electric field. Further out, these lines are more spread out. So that signifies a weaker electric field. So this field line diagram does indirectly show the strength of the electric field based on how close or far the lines are from each other. On the other hand, if we had a negative source, we'd expect the lines to be, electric field lines to be pointing inwards. Because again, the electric field is the force that would be felt by a 1 Coulomb positive charge. You put a 1 coulomb positive charge near a negative charge, it gets pulled inwards. You get an attractive force. So you'd have field lines pointing straight inwards in all directions, or from all directions. So that gives you an idea about direction. Electric field lines should be pointing outwards from a positive source and or inwards towards a negative source. As for strength, what do you think is going to determine how strong the electric field is from a point source like this? Like, let's say you wanted to actually calculate the electric field at this location. We know the direction. What would influence the magnitude? How strong the electric field is?
How spread apart the lines are?
Geometrically, yeah, we can look at it in terms of how far apart the lines are. But what is it about this location in space? Like if we didn't already have the field line diagram, what is going to influence how strong the electric field physically is? Are there any properties of the source object that you would think would influence how strong the electric field is?
Does it have to do something with R, like the distance?
Yeah, if you're like, let's say you're very close to the source charge, would you expect a stronger or weaker electric field?
Would be stronger?
Yeah, the closer you get to the source, the stronger the influence is. In fact, that usually seems to be true for a lot of phenomena, whether it's electric fields or magnetic fields or gravity. The closer you are to the source, the stronger the field is going to be. Whereas if you get further out, it's going to get weaker and weaker. So in our formula, and let's take a look at this in terms of just magnitude of electric field, because we already know the direction should be pointing away from a positive source or towards a negative source. But the magnitude, since it looks like it's inversely proportional to a distance, like the closer you are, the smaller the distance is, the stronger E is. The larger R is, the weaker E is. So radius, and we call this radius because it's a distance outwards from a center, just like the radius of a circle. Radius should go in the denominator. And it turns out to get the units to work out right, this needs to be R squared. So we've got an R squared representing the fact that the larger the radius is, the further you are from the source, the weaker the electric field will be. Also, let's say you're a certain distance from a source charge, or maybe you're a certain distance from another source charge. What other properties of the source charge itself could make a difference in how much electric field you get? Is every source charge identical?
Would it be Q or?
Q, the charge itself. If you've got a very large amount of charge here, like thousands of coulombs or something, you're going to get a very strong electric field. If you have a much smaller charge, just like a few coulombs, you're going to get a weaker electric field, even if it's the same distance. So more charge means a stronger electric field. So we put charge in the denominator here. So more charge means a stronger electric field. Further from the charge means a weaker electric field. And there's also, to get the units to work out right, a constant of proportionality called K. K is the universal electrical constant. And that's largely just to get the units to work out right and all the numbers to work out properly. But the important thing here is that the electric field strength, the magnitude, is proportional to charge and inversely proportional to distance squared. Also, I should probably put charge in absolute value here because we're just looking for magnitude. We don't care about direction yet. But this should work anytime the electric field is being created by just one single point charge. If you've got a more complicated cluster of charges creating the electric field, like maybe you've got a wire with charges all along it, or maybe you've got a plate or a wall that has charge on it, then it's going to be more complicated. But if you have just a single point of charge creating an electric field, this is the formula you'd use for how strong the electric field is. And if you've got, let's say, just a few point charges, like let's say you've got this point charge and this point charge and this point charge, and you want to find the electric field at some other location, you can just use this formula to find the electric field at that location from each point charge, and then use vector addition to add them together. So electric fields do add together using vector addition. We usually call that superposition, the idea that these effects add together, almost like interference for waves. You've got several sources trying to create an effect at some location, so you add those together to get the total effect there. But in this case, we're adding them as vectors because electric field is a vector quantity. Any other questions on that so far? All right, then that's it for now. Feel free to email me if you have any other questions. And again, take a look at those resources I put on math.ncheese.org/P7C if you want to review that. You're welcome. I'll see you next time.